Hello. This video we are going to talk about the experiment of the atomic emission determination of lithium. On the left you see the spectrometer that we'll be using, and on the right you see some pretty fireworks. And fireworks have been known for a couple millennia, and the different colors that you see come from the different metal salts that are in the fireworks. For example, barium gives you a green color, sodium a yellow color, strontium a red color, copper a blue color, titanium the white color. So why is this? Well, it goes back to the phenomenon of atomic emission, where we're having thermal excitation take place, where some metal that we'll call generically M, by absorbing heat gets excited, and then that's noted by the M star, and then it radiatively decays to a lower energy level, giving off a photon of light. Here you can see that transmission going down from the excited state down to the ground state, something that you learned way back in Chem 111. And so each element has different electronic energy levels and hence different wavelengths of light that you see, different colors that you see. The instrument that we'll be using is an atomic emission spectrometer, and if we were use atomic absorption, you have a hollow cathode lamp that's included in here, but we won't be doing that. What we'll do is aspirate a sample that you see in the bottom left from the little volumetric flask, and then it goes through a burner where the flame is made from acetylene, which is a fuel, and the air has oxygen in it, which is the oxidant. We actually throw away most of our sample, and we generate droplets that go up into the flame, and they're excited. There's a light that's given off by the flame and by whatever all the elements that might be in the sample. And so we need to separate that out, a wavelength sorter, and that's what we call a monochromator. And there you see the light coming off the grating and dispersing into the different colors of the spectrum. And then we need to electronically detect how many photons we have, and we use that with a photomultiplier tube. And then there's an electronic readout that comes along. So what happens is that we're going to take the bulk solution, put it up into the burner that we'll see in just a moment, and a process is called nebulization. We're going from solution to just small droplets. And the reason we're wanting small droplets is that we need to evaporate those droplets and get the atoms excited. And so we're in the flame, the process known as desolvation takes place, where that liquid droplet, the water, the solvent is evaporated, and we now have a solid that's left, metal salt. It's listed as MX. And then the salt gets liquefied and vaporized all the way to the metal, as we just simply heat it up from the thermal energy of the flame that could be in the neighborhood of 3,000 Kelvin or better. And then the energy from the flame is breaking that metal salt apart into the metal atom, which is what we want, and then the counter ion that's present. A process called atomization. And then excitation comes along, where that metal atom gains even more energy from the flame and becomes excited. In the previous slide we saw where it can give, as it goes back down to ground state, it gives off some light, and that's the atomic emission process. If we keep putting energy into it, we can actually have it ionize, where it loses an electron. That's something we want to actually avoid. The picture that you see is from Gary Hefia's lab at the Indiana University, and it shows a flame, and you see the droplets that are being injected that come in from the left, and they slowly get smaller. And the way they're doing this is by using a strobe light behind it. And so you can actually see the droplets spread out as they're accelerating the flame, and they get smaller and smaller. And so that's the desolvation process that's taking place. Then there's this section of the flame where you don't see anything, and that's where atomization is occurring. And then the excitation, you can see it's also occurring there. And the excitation, and then the emission, the light that's being given off up at the top, that reddish light. Really neat picture of all these different steps that are happening within the flame as it goes from the sample to the signal that we will want to record with our instrument. So here's a picture of the burner head, and on the and then a schematic diagram of it. And so the sample comes in from the bottom left if you're looking at the schematic on the right, and the fuel and the oxygen or compressed gases are coming in at a high pressure, so that actually creates a vacuum. And so the sample is aspirated through a small plastic tube. If you look at the color picture on the left, you can see down toward the bottom left center, you can see this little white tube, and that's what you place into your sample. And so it aspirates or sucks your sample up into the burner. There's a glass bead impinger where the droplets come out and hit, and they get shattered into smaller drops. Baffles keep the large drops from going onto the flame, and so they come back down and go to the drain. And so as we mentioned, we're actually throwing away a good part of our sample, and then only the smallest drops actually go up into the flame. We want small drops because the flame only has a certain amount of energy to it, and all those different steps that we saw earlier of going from nebulization all the way up to atomization and excitation, all that energy has to come from the flame in the short time that our sample resides in the flame as it accelerates through. So here you see a couple photos of the burner in action. On the left, you just see a blue flame, and that is from the carbon molecular combustion from our acetylene. If you got a gas oven at home or have used a backpacker stove, you've noticed this blue flame, or a Bunsen burner for that matter. And on the right, you can actually see our sample being aspirated in the flame and the emission signal, that red color that you see being given off by the flame. In this experiment, we're going to be using a new concentration term, at least in terms of the lab. We're going to be using parts per million. And so it was defined as is the mass of substance divided by the mass of the sample times 10 to the 6. You're real familiar with percent, which means parts per hundred. This is ppm, parts per million. So we think of it in terms of that definition that we've just seen. Mass of substance divided by mass of sample is micrograms per gram. That is equal to 1 part per million. Remember, micro is the SI prefix for 10 to the minus 6, or 1/1,000,000th. So 1 ppm would be a microgram per gram. So we're going to be talking about liquids, aqueous liquids, in fact. And so when we're talking about very dilute aqueous solutions, the density of water being 1 gram per milliliter, now we can substitute milliliters for grams, because 1 gram is equal to 1 milliliter, density of water of 1 at approximately room temperature. And so now this ppm unit can be expressed as micrograms per milliliter. Or if we take and multiply the denominator and the numerator both by 1,000, you can think of it as milligrams per liter. All three of those terms are parts per million. We're going to be using a different type of pipette in this experiment. We're going to be using a pipette man. And you need to watch the video that's associated with this experiment to better learn how to use the pipette man and some of the things you need to avoid using it. But there's a push button up at the top that and it has different stops on it that we'll see in just a moment. There's also an ejector button. There's a thumb wheel that's used for adjusting the volume. There's a volume display. And then there's the shaft of the pipette, or also known as a tip holder, and then these disposable tips that go on the bottom. And so you'll need to watch the video and the particular pipette man that you're using to be able to determine how to read the volume correctly. But we're going to be using a P1000 pipette. And so the different readings on this that you see are the first digit is actually that the digit in red that you see. The 0 or the 1 refers to that very first digit, which would be the ones, tens, hundreds, thousands place in that P1000. And so that second digit is actually if you think of it in terms of milliliters, it's after the decimal point, the first place after the decimal point. So the 020 is read as 200 microliters. And then the 075 is 750 microliters. And the 100 is 1,000 microliters, or 1 milliliter. And so the red numbers are to the left of the decimal point if you think of these in terms of milliliters, and the black numbers are to the right of the decimal point if you think of this in terms of milliliters. Once again, I want to encourage you to watch the video about using a pipette man, but that push button at the top has 3 positions. It has a rest position when it's all the way out. As you push it down steadily and slowly, you'll come to a first stop, and then you'll come to a second stop. And that's that blue button that you see there. The other small white button to the right, that's the eject button. And so it's important that you learn what those stops mean and how to use this pipette. So watch the other video to find that out. You'll need to calibrate your micropipette, and we'll use distilled water to do that, and our balance, and you'll be doing mass measurements. You'll need to know the temperature of your water in order to accurately do this. And so you'll want to develop a chart that looks something like this on a spreadsheet. And you might notice that the smaller the volume, the greater the percent difference. So micropipettes are least accurate close to the minimum or smallest volume, which makes sense when you just think about relative error in general. And so there are actually 2 calibration plots that you will be generating for this experiment. One will be for your micropipette, where the y-axis will be the actual volume that you determine from the mass that you have measured, and the x-axis will be the micropipette reading in microliters. And you can see the slope of the line that's generated and the r-squared value that is generated for this particular set of data that was used to make this plot. You'll want to do the same thing. So we're making 2 calibration curves. First one for the micropipette, as we just mentioned, and then you'll be making a second calibration curve that's actually for your unknown, for your lithium atomic emission. And so you'll want to recalculate your actual standard concentrations using the corrected volumes from the micropipette. And so, for example, using the calibration data on the previous slide, when the micropipette is adjusted to 100 microliters, it's actually pipetting 104.1 microliters on the average. So if 1 ppm standard was prepared by diluting 100 microliters of 1,000 ppm standard to 100 milliliters, what would the actual volume be? I'll let you think about that. Throughout the course of this, you're going to be using C1V1 equals C2V2 formula for dilutions. So 1,000 microliters times 0.1014 milliliters is equal to C2 divided by 100 microliters. And so your actual concentration would be 1.041 ppm. And so you'll have to repeat this calculation for each solution. And so you can use Excel to do this and very quickly, repeated times. And so the calibration curve that you'll generate for lithium will be how you will actually determine your unknown by using Excel and the LINES function to generate the slope and intercept. Safety considerations to think about. When we're using this flame atomic emission spectrometer, you have to worry about thermal burns, flashback of the flame, and there's compressed gas safety considerations to take into consideration since we will be using compressed gas. Your instructor will be there to help you along the way. The lithium solution is corrosive. It was prepared with an acid, so wear your gloves and your PPE as usual, and all solutions can go down the drain. So have fun with this lab. It's a fun instrument to use, and happy calculating afterwards.